semester. Today our speaker is Dr. Jim Napolitano, who's joining us today from Rensselaer Polytechnic, and he'll be talking about the latest results from Daya.
Thank you.
Please welcome our speaker.
It's nice to be back here. Last time I was here was 21 years ago, 22 years ago. Things have changed a bit. We actually have a kind of nice connection with Texas A&M. I want to mention, Ed walked in a minute ago and said, I said, "Oh, Ed Fry." He said, "How did you know it was me?" And I said, "You'll see." Ed was really very, very nice. Back in the days when we were just starting this experiment trying to figure out how to purify large amounts of water and keep it pure, we were using some paper from him that measured the transmissivity of water, and I contacted him by email, and he was real helpful, and he got back, and he apologized for not getting back sooner. And wow, this is department head, so I'm busy with it. It was really nice. It was actually very helpful. And the other is John Mason, who's sitting over there. John was an undergrad at RPI and started this stuff early on. In fact, he took our freshman honors physics course with me. We were talking about research, and one day after class, he comes up and says, "I want to go to China." And I said, "Well, we'll see, we'll see." But he did, and there's a picture of John in front of the assembly building, surface assembly building in China, and spent some time there and taught people how you get hamburgers on 4th of July. Experience. Okay, so here's the outline. I'll tell you some introductory stuff about neutrino oscillations. I noticed that not a lot of that goes on here, so I thought it'd be a good idea to point out a few things to people. What we're really measuring is mixing angle theta 1,3, and I'll tell you about that. And then I'll give you lots of details on the experiments. There's lots and lots of stuff I can talk to you about. We really do have quite a bit of details. So if there are things you don't see, have questions about, please ask. Ask questions at any time. I can flip around stuff and drag up whole stuff if we need to. I'll take a few minutes afterwards to tell you about where I think this stuff is going. All right, so this is a picture of the universe, something called the Hubble Ultra Deep Field. It's a really neat photograph. You pick a really dark part of the sky with almost no stars in it, and you take a long exposure photo. They call this the ultra deep field. You can pick out the stars in this photograph. There aren't very many because you can see the little diffraction spikes because they are point sources of light. Everything else in this photograph is a galaxy. And every one of those galaxies, the best we could tell, is made out of matter, not antimatter. The universe is made out of matter. We all know this. We talked about it, the so-called Baryony symmetry problem. Why is it after the Big Bang we ended up with 1 billionth extra particles instead of photons or baryons, not antibaryons? The only way to understand that is through CP violation. Something happened in the early universe that didn't respect CP. And you can look at this nice paper by Sakharov where he showed that you cannot account for it with quarks. And we know that there's CP violation in the quarks, but there's not enough there. You can't explain why the universe exists based on stuff we already know, at least phenomenologically. We know it has to be antimatter, and there's real reason to believe that neutrinos are responsible. That's what it says on the bottom. Are neutrinos responsible? We're betting that they are. We're betting that the seesaw mechanism is giving us the right idea of where the neutrino masses are, and that may be the key to CP violation. So that's what we're doing. That's the holy grail to us, is to try and understand CP violation in the neutrino sector. All right. We have this mixing matrix, which they call MNSP. The P is Pontecorvo. I forget what MNS means. It's just like the CKM matrix, Cabibbo mixing, right? 3-generation Cabibbo mixing from Kobayashi and Moskawa. And so you have this unitary matrix. It mixes up individual mass eigenstates with the flavors that we call electron, muon, and tau neutrinos. And that's what we're trying to measure. Just like the CKM matrix, you can parameterize that with 4 real parameters. 3 angles that we call theta 2,3, theta 1,3, and theta 1,2, and one phase, right? That phase is responsible for CP violation. In fact, this matrix was invented to contain CP violation and be the phenomenological way that it was incorporated into quarks and also into neutrinos. we write this matrix, you can parameterize these matrices any way you want. The CKM matrix is parameterized very differently. The three angles in the phase are hidden in different ways. Here it's broken up into three 2x2 matrices essentially. And because when this was being put together, these two look like they were relatively large angles, theta 1,3 might be small, it's written in such a way to marry that CP violation to theta 1,3. Because if theta 1,3 was 0, that's just the identity matrix, and there is no CP violation, and you've got to go somewhere else in neutrinos, presumably, to figure out where the universe came from. So the effort that I'm going to tell you about was to measure this angle, prove that it was non-zero, and figure out what its value is. We know that's the case, and you've heard about that before. The next step is to try and figure out delta, and I will conclude by showing you what I think the landscape looks like for that CP violating phase. Okay? So that's what we're about. I guess I pretty much told you about that. Those are the parameters. We measure these things using neutrino oscillations. This is a phenomenon that we make use of to measure those four parameters. All right? So neutrino mixing is the thing we're trying to learn. Neutrino oscillations is, in our case, the technique that we use to try and measure them. Neutrino oscillation says, okay, I'm going to create a neutrino in a certain flavor, let it travel some distance, right? And then detect either that flavor or another flavor. And then ask yourself, what's the probability that if I start it in flavor state A and then measure it in flavor state B, what's the probability? And the answer is straightforward. You just take that state B and project the time evolved state A onto that. This is just quantum mechanics 101. That state evolves according to a Hamiltonian. And if I take this and then insert the mass eigenstates, I end up getting an expression that looks like this at the bottom. So it's a straightforward calculation. You can write it down in terms of the matrix elements, UIJ. This is a mess. To try and write this down in general would take a page, and it would not be very useful to you at all. So what I'm going to talk to you about are special cases of this, and the special case that I'm going to talk about in particular is so-called neutrino disappearance, where we're going to start with a source of flavor nu A, let it go over some baseline L. Neutrinos are very lightweight, right? So they basically move at the speed of light. So the time that it takes for things to evolve is just that baseline divided by C. And we're going to try and detect the same neutrino that we created. All right? If they disappear, then it's evidence for neutrino oscillations. And what I'll be showing you is our first result, which says, yes, neutrinos disappear. And then I'll show you something we released just a month ago that shows they disappear with energy in a way that's completely consistent with neutrino oscillations. So you take that complicated formula on the previous slide, and instead you reduce it down to this neutrino disappearance, and essentially you get this expression. Now I'm lying to you a little bit here. This is a simplified, sloppy way to look at the expression. I'll give you the full expression in a little while, but I want to accentuate what really comes out of it. This is really three terms, right? One for each of the three different pairings, 1, 2, 2, 3, and 1, 3. We're going to accentuate one of those particular terms by selecting a baseline for a certain energy that's commensurate with the difference of the squares of the masses of the ones that I'm trying to identify. So you want this oscillating term to be maximized. You do that by making this thing equal to whatever, pi, all right, or pi over 2. And that'll give you a maximum oscillation. Measuring the amplitude of that oscillation, that disappearance, tells you sine squared of the mixing angle. The trick is to make sure that L over E is the right value for what delta M squared is. And no one knew what delta M squared was until we did a bunch of experiments. But let me show you what some examples look like. This is a beautiful experiment called T2K in Japan. In Japan, I guess the beams go from right to left. So here's the accelerator, J-Park, right? It produces a bunch of pions, and those decay to muons and muon neutrinos. They fly 300 kilometers across Japan to the Super K detector, which is inside a mountain. Big water detector. J-Park's a nice facility, which is unfortunately close to Sendai and was shut off during the earthquake and the tsunami, but things are back up and running again. Very straightforward once you know what you're doing. This is what the energy spectrum looks like of the muon neutrinos they detect. So you start with a muon neutrino beam, you look for muon neutrinos. And this black line is what you expect. There's a detector right up close to the target, to the neutrino source that measures the shape of the neutrino spectrum. So you know what you're supposed to expect. You propagate that over that distance. What you expect to see is this. If there are no oscillations, what you actually see is the red curve. They're pretty much all gone, right? With a dependence on energy that agrees with the best fit that you get if you're measuring neutrino oscillations. And after you do that work, you end up with this as a best value for theta 23. L over E in this case is about 1,000 kilometers per GeV. By the way, you want to keep in mind that 1 kilometer per GeV is equal to 1 meter per MeV, because with reactors we have about MeV of energy for the neutrinos, not GeVs. Nevertheless, it all works out. You end up seeing this huge effect, big oscillation when you're at the right distance to pin that difference in mass squareds. Okay. Here's another example. This one is 2 to 3 oscillations. That's what it says up at the top. 2 to 3 oscillations. Here's a different example. Experiment is called CAMLAND, which is sensitive to oscillations between 1 and 2. CAMLAND is an experiment done with, also in Japan, using nuclear reactors. Nuclear reactors, I'll show you a little more about that later, but they turn nuclei into nuclei. It makes a lot of neutron-rich nuclei, so it turns neutrons into protons, and the net result of that is to give you electron antineutrinos. So it makes electron antineutrinos. There was this cavern in this mountain, Tamioka, which is where they built the first Tamioka nucleon decay experiment. It turns out that if you look at all the nuclear reactors in Japan, they were all about, concentrated in a distance of about 150 kilometers away from that mine. What a lucky thing, all right? You build a detector there with about 4 MeV of energy. L over E turns out to be about 5 times 10 to the 4th meters per MeV, so about 50 times larger than the T2K experiment, sensitive therefore to much smaller values of delta M squared. In this case, what we call 1, 2, delta M squared between 1 and 2. And once again, you see an enormous effect. This is the spectrum that you expect from the nuclear reactors. This is the spectrum of function of neutrino energy that CAMLAND sees. If you divide these, you actually get a nice oscillation curve as a function of energy. Really looks like neutrino oscillations. Beautiful. And it's a huge effect. Once again, that mixing angle is very, very large. You see a very large effect. In fact, CAMLAND is sitting a little too far. Ideally, you'd like to put an experiment here and maximize the effect, but that's where they put the nuclear reactors so you make good use of it. These are a bunch of other reactor experiments, all of which saw no effect because they were too close. The experiment I'm going to talk to you about sits right here. That's where about Daya is. That's where we expected to see an effect, because that's the delta M squared that corresponds to 2, 3. Since the 1, 2 mass squared is real small, the 2, 3 mass squared is a lot bigger, then the difference between 1 and 3 is pretty much the same as 2 and 3. And that's how we designed the experiment, and that's right here. In fact, that experiment called SHOW should have seen something, but their simulator crapped out and died, and that was all she wrote. For the students especially, I'd like to make a point. Got to keep your eyes open, keep an open mind. This is a huge effect. If neutrino oscillation is so big, why did it take us 4 or 5 decades to finally observe it? Those delta M squares are really nasty, right? 1, 2 is so small, I had to go far away. 2, 3 is small enough. To design an experiment to do that, you need a really good reason. And the real heroes in this are the people who measured the solar neutrino experiment, Ray Davis, John McCall, the Sudbury Neutrino Observatory, and Super-K did really nice work in the solar neutrino problem and the atmospheric neutrino anomaly. It's a wonderful colloquium, Great thing for students to read about and learn. It's one of these experiences where you gotta believe that you see something weird, it might actually mean something. Those were the hints we had for decades that there were neutrino oscillations. It took a long time to follow up and actually prove it. So in about 2010, this is what the Neptune Matrix looked like. Looks entirely different than quarks. That was the mass difference squared. Very big mixing angles for 2, 3, and 1, 2. But the value for theta 1, 3 looked very small. And this was a crisis, right? If that angle was 0, I was one of the people who was betting it was 0, then CP violation does not happen in neutrinos, and you got to figure out some of the reason why we're here, right? It turns out that the right value was just under the limit. Just under the limit. Those guys at show probably should have observed it, but it was a little bit too small. And that's what I'll be telling you about. There were some hints. Oh yeah, this is the experiment from show. That's about where the limit is. I'll tell you more about reactors about that. There were some hints. It turns out Chemland actually depends a little bit on theta 1, 3 as well as 1, 2. So it's got a little bit of a tilted contour. The solar neutrinos really only depended on 1, 2. And the intersection of those two contours suggested a non-zero value for theta 1, 3. It turns out it's right on top of that dot is where the right answer is. But we didn't know that at the time, of course. Everyone started hunting for theta 1, 3. 3 reactor experiments were set up. One was called Double Show in France. The other is called Reno in Korea. And the experiment I'll tell you about, namely Daya. There were also accelerator experiments going up. I showed you T2K's nu mu to nu mu disappearance. The way to be sensitive to theta 1, 3 is to look for electron neutrinos appearing out of that beam. That would be sensitive to theta 1, 3. NOVA was built, in fact, the NOVA is the neutrino, NUMI, damn it, why am I forgetting this? NUMI oscillation, neutrino appearance. The A is appearance is the point. T2K is a great big experiment. They were also able to do neutrino appearance, but they had a water detector. It's not as sexy as this, it's a little harder, but they had it running. I'll show you what that stuff looks like later. But now what I want to tell you about is Daya Bay. Daya Bay means Big Bay. The picture of it has a guy with his hands out like big. It's in China. I'll show you where it is. This is what the nuclear reactor complex looks like. It's right on the Pacific Ocean in this great big bay. Notice that the mountains rise behind the nuclear reactors. Turns out that was really pretty important to get the whole thing set up. And I'll show you the layout in a second. We really are a global collaboration between Asia, US, and Europe. Big reactors, 17 gigawatts thermal. For those of you who know about nuclear reactors, that's an awful lot of nuclear reactor power. I think it's the 7th most powerful reactor complex in the world, something like that. Our goal is to get around this hard problem of knowing what the neutrino spectrum is by putting detectors close and far. Close to the detector, you measure it like T2K did with their beam. Far away is where the oscillation is. That was always the limiting thing, trying to figure out what the neutrino spectrum was. Our detectors are in tunnels inside those mountains, and we designed everything to do a 1% experiment. Statistics would be better than 1%, so every systematic we had in the experiment we wanted to control to the 10th of a percent level. That was our goal in everything. Mass, relative efficiencies, everything. It's challenging, but that was where everything was designed. And the thing that's kind of hidden is just a NEM reference that describes the detectors. So here's where it is. Daya Bay is up here. This is the administrative boundary that is Hong Kong. Just over that boundary is the city of Shenzhen, which I'm told was a fishing village 30 years ago. So you travel to Daya Bay by taking the train from Hong Kong to Shenzhen, and then our driver, Mr. Liu, picks you up, and then John taught Mr. Liu how to have hamburgers on the 4th of July. It was a challenge. You get ground beef. Anyway, he picks you up at Shenzhen and then drives you to the site of Daya Bay. And remember, you guys, please, questions. If you have questions, ask them. Usually what we do is fly, if you have some time, spend the night in Hong Kong, try and recover a little bit before you make the trip out to Daya Bay afterwards, about 2-hour drive.
Do you know meaning of the one?
Sorry?
Do you know meaning of the one? Yeah, one.
I thought one was Bay. Or
Yeah, that's
yeah.
right.
Yeah, and all the Chinese is Daya one. I get used to that. Good. So here's a Google Earth shot with some things on top of it. So once again, here's the bay. There are 3 reactor cores, actually 3 pairs of reactor cores that we refer to as Daya Bay, Lingyao 1 and Lingyao 2. The experiment is set up so that we have 2 detectors. The data that I'll tell you about has 2 detectors close to the Daya Bay cores, 1 detector in the mountains close to the Lingyao cores, and 3 detectors far away. This is the baseline, about 1.6, 1.7 kilometers, that optimizes the oscillation based on delta m squared 2.3, which should be the same as 1.3. There are all these tunnels that you get things from one place to another. I refer to them frequently as Hall 1, Hall 2, and Hall 3. I've listed here the amount of overburden in meters water equivalent over the detectors. This is more overburden than the other 2 reactor experiments, and I'll show you how that made a difference for us. It's one of the reasons our experiment worked so nicely. Yeah.
Only Hall 2 has only one detector.
Well, they only had 1 because we got things up and running quickly. In the summer of 2012, we installed the 2nd detector here and the 4th detector here. That's what we're running with now. That data hasn't been analyzed for public consumption yet. Okay, good. So, reactors make electron antineutrinos. The basic idea is that neutrons are turning into protons, electrons, and Dewey bars. But it's not free neutrons. They're happening inside complex nuclei. Nuclei that come from the fission of something very heavy like uranium, although there are other isotopes as well. The fission fragments have a distribution. Most of them are completely unknown. Right? We don't know what they are. We don't know what their beta decay endpoints are. We don't know what comes out of them. You can only make estimates. And if you look, Jerry Garvey, in fact, not too long ago, Jim Friars and people in Los Alamos pointed out that all these mistakes are being made in how people calculate the spectrum of neutrinos from a reactor. Well, nuclear physicsy, but they assume all the decays are allowed beta decays. And they made some estimates of what happens if you let them be forbidden beta decays, and you get some real serious changes. So trying to understand the neutrino spectrum is very, very hard. All we know is that we're making electron antineutrinos. That's the basic point. You get it not only from uranium, but the neutrons capture on uranium-238 that make plutonium-239. That fissions. Also plutonium-241. They have roughly the same shapes, but on this log scale, they're significantly different. And then, as the reactor goes on in time, the relative amounts of those different things changes. So the details of the spectrum depend on time, core composition, and a bunch of things you don't know about. It's a hell of a difficult problem. And our approach was basically not to bother by measuring it, not to bother calculating it, but instead just measure it. So here's roughly what the spectrum looks like for neutrinos. This is what the cross-section looks like. You expect to get a signal that looks something like that, right? That's the basic idea. That's what we'll be looking for in our detectors. We detect electron antineutrinos in the classic way, pretty much. And remember, neutrino interactions are rare. In our far detectors, we see about 100 events a day. Lots of other backgrounds going on. We've got to beat back those backgrounds. What do we see? Well, we have great big vats of liquid simulator that I'll show you. The Dewey bar comes in, hits a proton, turns it into a neutron, pops out a positron. That positron is critical for us. That's our signal. That's the thing that tells you the neutrino energy. That's the thing that says you detected the neutrino. Problem is, it goes about that far in liquid simulator. Lots of other backgrounds will simulate that. You gotta know that you saw a neutrino event and not some random piece of crap in your gauge detector. What we use is we load the simulator with about 0.1% gadolinium, which had some interesting chemistry associated with it. The neutron rattles around and eventually captures on a gadolinium nucleus, makes a splash of 8 MeV of energy, and we call that a delayed signal to distinguish it from the prompt positron. That prompt plus delayed coincidence is what tells you that you had a neutrino event, and I'll show you how that works in a bit. So here's what our detectors look like. So we have 6 of these deployed in the data that I showed you, 8 of them eventually, all built in more or less identical pairs. It's called a 3-zone anti-neutrino detector because we have the central part, which is gadolinium loaded. Outside of that, we have another vessel that has just liquid scintillator. We call that a gamma catcher, right? The neutron captures on a gadolinium. Those photons might get out a little bit. We want there to be scintillator around the outside to catch them effectively. And then we isolate all of that from the phototubes on the outside to have to define our fiducial volume nicely. And this is all filled with liquid scintillator, mineral oil in this outer zone here. There's 20 tons of active gadolinium-loaded scintillator in the center, so we have 8 20-ton fiducial detectors. Yeah, the dimensions. This is 5 meters by 5 meters is the big detector. There are these calibration devices on top. 4-meter cylinder on the inside, and then the farthest inside, holding the gadolinium-loaded scintillator, is a 3-meter acrylic vessel. Oh boy, I'd love to take you through all this, but I'll just show you very quickly. This is the what do you call them, those Russian dolls where you put things together. So I'm assembling this thing. The acrylic is really pretty cool to look at. They're all assembled in this pit. That's the building. It's in that building that John was standing in front of. And then they get carted off to the nether regions in this big contraption that I can tell you stories about. Transports the detectors through the tunnel, all loaded up with scintillator. Well, actually, they leave the assembly building. They go underground where they get filled up with liquid scintillator and then run. This is a little technical, but since my graduate student did the work, I figure I should show it to you. We use, well, actually, there's some important stories about this. New scintillators had to be developed to do this. We're putting them all underground, and there are issues having to do with fire safety. You work underground, you learn about these sorts of things. Linear alkyl benzene is basically a detergent that you can dope and have it be scintillator properties, and it's got a very high flash point. So it's much safer than a lot of the liquid scintillators people are used to using. It's also pretty cheap. Was learned how to dope it with gadolinium at 0.1%. But then the issue becomes, what is the attenuation length? And these measurements showed that LAB has very long attenuation length, close to 50 meters. You dope it to make it scintillator, it still keeps it. You add the gadolinium, it goes down some, but we still have attenuation lengths in excess of 30 meters. So in a 5-meter detector, that's pretty clear. So that was pretty useful to us, and confirming that was important. That's at 470 nanometers. It gets shorter at shorter wavelengths, but we put all those models in to figure things out. Big facility underground for filling liquid scintillator, and this, boy, there are stories I can tell you about safety that I won't, maybe later. I mentioned the show experiment had to shut off. Were you around when we had that problem? The fire? They filled all the vats underground with liquid scintillator, and someone pointed out that no one had turned on the fire safety system yet. And the U.S. safety person said every U.S. person has to leave the site.
No, I was there.
You were there for that?
I was there for that, yeah.
That was a lot of fun. Anyway. I mentioned the show experiment. They had to shut off because their scintillator was turning brown. Putting gadolinium into scintillator is tricky, and chemical reactions happen, I don't understand, and the stuff will die over time. One of the things we were terribly afraid of, had to make sure that didn't happen to us, and the smart chemists were able to figure this out so it's not going to happen. In the end, this is what we got. Now, you can't see it, but degradation is in quotation marks up here. This is our calibration over, so this is January 2012 through December 2012. So this is 1 year's time. This is the energy scale for the calibration at photoelectrons per MeV. Big suppressed 0, right? This is 165 to 170. We see a steady decrease over time. We're not 100% sure this is due to the scintillator browning. But if it is, that's okay. because it's a 1% change over a year. We can deal with that, we can calibrate it out, it's not destroying the simulator. We got better at this after a while, not quite sure why. The fall off is right, but the amount is higher. We don't really understand that effect, but we can calibrate it out, and we're not worried about the simulator turning ground on us. So now we're getting a little closer to the part of the experiment that was near and dear to my heart. Backgrounds are important, right? We've got this nice delayed neutron to kill off some backgrounds. We still got to make sure we know what's going on and keep their general backgrounds low. And the approach in this experiment, which sounded nuts to me when I first heard it, but it worked out really well, was to take the detectors and immerse them in an enormous swimming pool of water. The water provides passive shielding from the radioactivity on the outside. And then by instrumenting the water with phototubes, you can use it as active shield to detect muons that pass through. And that was how I got in touch with Ed, because our job in my group was to make the purified water for this thing. And it all worked out pretty well in the end. When you put it all together, this is what it looks like. This is that pool with those 3 detectors, and here's the water. I would love to understand why the water looks so blue. But it turns out that's very pure water. For those of you in the know, we now understand that the water in the pool is about 5 megohm centimeters, and instead of the limit, which is about 18 for resistivity, we think that it's got to do with carbon dioxide leaking in from microorganisms that are growing on the outside of the pool. We have to shut the experiment off for a couple days to get samples to prove that, and we have a task control form ready for that, but I don't know what we're really doing it. The point is it works pretty well. The blue color we think is from the fluorescent lights or something. You know, I was definitely afraid that as soon as you fill this up with water, you'll see little bubbles of mineral oil coming up out of this thing, and you're like, my God, they're leaching work, but it never happened. It was designed beautifully, everything worked really, really well. The passive shielding is really great. This is one of our first fills with the detectors in the Daya hall. There's only 2 of them. As this thing is getting filled up, this is what some of the data look like. So this purple boundary here is the 4-meter acrylic vessel, which is where we have all the scintillator. The water comes up to here in the data that was taken here. You can really see that the position of all of our noise background events is much, much reduced underneath the water than the top. So as it fills up, it really is shielding us away from all of that radioactivity, getting our singles rates down. There's a really nice Rube Goldberg machine to put together this muon veto shield with a photovoltaic wire tube and the router, and I'm going to go through that. But boy, that was a lot of work. You weren't there for that. And you can see that that the muon rates coming through the shield are about 100 to 200 per second. In the near halls, the far hall, which is under much more mountain. That was one of the nice things about the experiment. You get farther away from the reactors, the mountains rise away from the shore, so as your rates goes down, your shielding goes up, and that more or less cancels each other out. So you can really see that the rates reduce by an order of magnitude when you get outside. Okay, so now how the experiment works. So I'm reminding you, I showed you this before. We have 2 signals, a prompt signal from the positron, a delayed signal from the gadolinium. And I'm going to show you several plots now that compare the 2 detectors that are close to each other in the so-called diagonal. Yes?
Can you go back to the
Sure.
Yes, I mean, it looks like most of your detector is designed to detect a neutron, right?
Yeah.
Primarily. And then, but the gadolinium capture cross-section is very high for thermal neutrons. Low
That's
energy.
right.
And in your 2-body decay, I mean, this positron plus neutron,
That's right.
not all of them are thermal neutrons.
That's right. None of them are. Almost none of them are.
And so
They have to thermalize. That's what these bounces are like.
So that scintillator is not very good at thermalizing. You might have considered filling it with water, for example, or gadolinium loaded water. Why not gadolinium loaded?
I wasn't part of the experiment when that stuff was cast about. I don't know if they looked at it. I know you get a lot more light, obviously, out of the scintillator than you would out of water. You might have been able to dope the water. I'm not sure if those options were investigated.
Because the efficiency of thermalizing the neutron is very poor.
Let me show you, actually, because that was one of the things. I want to show you different detectors, and in fact, what your answer is in the next slide. Just to show you, each of these plots has both red and blue points on them, but they're more or less on top of each other. These are the two detectors in the Daya Bay Hall, and you really get pretty much identical signals. So this is all of our triggers. Here's all the resulting signals noise. After we apply a muon veto, it gets rid of this stuff, but this stuff still remains. But this is the neutron capture time. So this is how well it thermalizes, all right? We put a cut of, I think, about 100 microseconds. So this time scale is microseconds. And part of the design was to make sure that whatever thermalization you get from the liquid simulator was enough. And this worked out okay. So the additional light that you get from simulator and the ability to deal with this kind of thermalization time was part of what convinced us, yeah, we'll go with simulator. I'm sure that was the consideration here. You could do it. You're right, water would be better to thermalize neutrons, but we need to see that positron clearly. It's real important.
You're worried about the neutrons just leaving and never getting in, never getting picked up,
Well,
right?
I mean, the neutron, the gadolinium does nothing unless you can thermalize the neutron.
Right.
Because the capture process is very, many orders of magnitude smaller. So as soon as they are thermalized, the neutron, the gadolinium works very well. But then once gadolinium captures, it's going to spew out NUV gammas, which are, but that's where you need the liquid simulator to convert.
Well, that's why we have the liquid simulator jacket, the so-called gamma catcher around the outside.
It seems like a little bit of luxury to have so much liquid simulator on the inside.
This experiment didn't really spare any expense. We're trying to do a 1% measurement here.
Oh,
Actually, I think the efficiency, in some sense, is those first 2 or 3 bins, right? Because all the ones that left are the ones that would have
left
been very,
here, right?
yeah, they would have left there. So you can, so it looks like you're actually getting a very large fraction of them because you're able to integrate out for so
So in
much.
other words, if I extrapolate this to 0,
Yeah.
those are the ones that I'm losing.
I think that's,
Yeah, it could be.
I mean, I don't know, maybe that's, I mean, it's log scale, so it's hard to tell, but it's maybe 40 or 50%. So,
Yeah.
I mean, you might have doubled, but you're getting high quality measurements of the stuff you do get.
I have the efficiencies later, we can take a look at them, but remember, we're always
Yeah, you're
making
probably
relative
right.
measurements here.
Right, but if you're at 1% statistics, doubling your statistics isn't gonna help that much, because you're also
Yeah. I don't know. Turns 3 years into a year and a half.
But it's all.
But we
it's all
gotta,
worried about your systematics.
we gotta get the systematics down.
Right. And this bias is systematic, I understand.
And again, these are two detectors. The fact that these are right on top of each other really worked nicely. We're able to get everything straight. So this is what things look like when you get down to the end and make the cuts on timing. This is the prompt energy. This is the delayed energy. This big blob here are gadolinium captures at 8 MeV. All right. So you take this blob, you project it onto that axis. That's your neutrino spectrum. Here's all the remaining noise. All right. There's some accidental coincidences. You can see the NP to D gamma, neutrons capturing on protons, sticks out as a signal. Some people are actually analyzing that as well. But this all worked very well. We were really glad when that came out. And this was the thing that really sold it for us. These are the two detectors right up near the Daya Bay reactor core. They look basically identical. When you take the ratio of those two, you get 0.987 plus or minus 0.008 statistically. Right? That's not 1. It's a little bit less than 1. These detectors are 5 meters apart. They're about 300 meters from the reactor core. What we're seeing is the difference, exactly the difference you expect from the fact of 1 over r squared falling out a little bit farther away. When we realized we were getting things that nice, we believed we had an experiment. We built detectors that could measure this stuff to 1%. So we rushed and got all the other detectors put together. Just to show you again, with those detectors, you can see the reactor cores turning on and off as they refueled and whatnot. That's such a big deal. Backgrounds, just to show you some of the numbers. Our signal of background of the near detectors was about 50 to 1, about half that from the far detectors, where the rates of neutrinos are smaller, but the backgrounds are smaller. One of the things that's interesting to note, and this is a little nuclear physicsy, is that we have a lot of overburden, and that really accounted for this really nasty background of lithium-9, helium-8. Those are isotopes that are produced from neutron spallation reactions in the detector, and they look just like neutrino events because they're a beta decay followed by a neutron ejected that's just sort of hanging out in the daughter nucleus that's left. Looks just like a neutrino signal. And the half-lives of these things are fractions of a second, so you can't veto your detector when you've got 100 hertz rate. But we can measure that decay very accurately and then subtract that and compare it to Monte Carlo. That all worked out beautifully. So we had all those background pins. So here are our results. So this is over something like a large piece of a year. This is the near Hall, your Daya Bay, the Lingao near Hall, and the far Hall. The green are, I'm sorry, green and red, that was bad. The green dotted line is the no oscillation prediction, and the red is the best fit. You can see that there's basically no difference between the two between those two and the two different near halls because they're really near, right? They're close enough so that the 1 over r squared dependence is not modulated so much by disappearance from oscillations. But this is what we see in the far Hall. I want to draw your attention to the fact that we turned on New Year's Eve, and then over a week's time, almost every data point was below what the prediction was. The postdocs were analyzing this data, and by New Year's Eve, we knew we saw something. We knew we were seeing neutrinos disappear. It was really exciting. A decision was made to publish based on data we get here, because that would give us a 5 sigma oscillation result. And we released the result in March, and there was this great big splash, and it was a lot of fun. I was chairing the speakers committee at the time, and I probably spent half my day fielding requests for talks. It was wonderful. Here are our efficiencies. Oh boy, do you want to spend much time on it? Probably not. If people want to come back to here what the efficiencies are, we can talk about this some more. Let's see. This is what the oscillation result then looks like just on the basis of rate. These are the near detectors, a small decrease. This is the expected fit. This is where we are at the far Hall. These 3 points are separated just so you can see them. All very consistent. Sine squared 2 theta is 0.09 to nice precision, and all dominated by statistics. There's really no systematic uncertainty because we made it really small. Because we were hoping that this might be 10 times smaller. That's what we were designing for. Just to show you what our spectra look like, this is at the far Hall. This is what the background contributions look like. One of the nice things that we included, we published in our first paper, was to show that the shape of the distortion with energy agrees. Remember, you get a spectrum of energies from a reactor. So L over E is different, even though you say L. So it was optimized for this energy. So you get less oscillation when you get away from that, and that fit was consistent with that. This is not a fit, right? This is the prediction. To actually do that right, you need to do your energy calibrations very carefully, which was finally done. And now I have to show you what I didn't show you before when I wrote down oscillations. The full expression for anti-Dutrient appearance looks like this. I took this delta M squared EE as actually 2 different terms, one for 1, 2, and one for 1, 3 rather, and one for 2, 3. And this is the way the whole thing works out. This is the term that Camland was sensitive to, but it's very small for us. We're optimizing on this term here. And this is what the numbers work out to between EE and 3.2. There's a sign difference here depending on whether the neutrinos are a so-called normal hierarchy, where this is normal hierarchy, where the first 2 are light and the third one is heavy, or inverted, where the third one is light and the other 2 are heavy. But the difference between them is maintained. And we don't know which one that is. That's one of the things we want to figure out next in the neutrino business. The energy calibration, as I mentioned, is critical. I'm not going to belabor it, but it took well over a year to get all this pinned, and this is what our calibration looks like. This is what boron 12 looks like, radioactive decay that is made spontaneously in the detector. our calibration, our resolution, and this is the correction that we have to get reconstructed from true energy. And at the worst case, it's something less than 10% correction, but it took a while to get all that stuff knocked out. A lot of different models were included to try and compare these to get our systematic error pinned. And in the end, we're able to fit the rate, including the shape. It doesn't improve very much on sine squared 2 theta. You don't expect it to. The uncertainty is basically the same. However, now we can actually measure the delta m squared from these experiments. And we get a value that's perfectly consistent with what we expect. This is the value that came from MINOS for delta m squared. This is our best fit value, clearly within one sigma contour. You can also say, hell, I don't care about the rate. I'm just going to compare the shapes. I'm going to look at the wiggles and fit the wiggles. You don't get nearly as much statistical power that way for sine squared theta. So this is not really a competitive measurement for sine squared 2 theta 1 3, but it's really nice to see that you get a perfectly consistent value of delta f squared. We're observing neutrino oscillations, and these fits make that clear. There's a story behind the next plot, which I'll tell you if you ask, but this is the way you want to plot this, right? You want to plot the oscillation probability as a function of L over E. And we can get this for our near detectors and for the far detectors. This is neutrino oscillations. This is that sine squared delta m squared L over E term. And it comes out right. So we're seeing neutrinos disappear. They are oscillating. A little bit of history. This was our first result that we released back in March of 2012. This double show had a result out beforehand, but all these are systematic uncertainties because they didn't have a near detector to measure the reactor flux. Reno came out right after us, confirmed our result. Things have been progressing over the years, and now this is Daya latest result, which basically is the PDG value. T2K has measured appearance.
Why are so many data points on a previous slide? So the firepower has 3 distances for 3 sets of nuclear reactors. So wouldn't that should be 3 data points?
No, the data points are gotten by binning energy, and the distance is an effective energy based on weighting the different reactor powers.
They're coming different energy bins.
Yes, they're all different energy bins. That's where all that stuff comes from. And knowing how those energy bins overlap relative to each other was all the hard work to get it right. If a postdoc hadn't shown that plot in the conference, and then everybody said, my God, we wanted to do this better, and all of a sudden all this work happened where everybody proved that we get the right answers, and now we can show this plot. And it'll show up in the PRL. We have a Pfizer athletic draft circulating in the collaboration. But now look at this. This is Daya, and this is T2K. And I'll show you their appearance experiment measurement in a second, but those don't exactly agree.
What's the difference for T2K between solid and dotted?
Normal hierarchy and inverted hierarchy.
Okay.
Right? It says that up there. So.
Oh, it does? Ah, okay, I see it.
It's okay, Carl. This is their experiment. They have to tell electron appearance from pi zeros that you get from muons, neutral current events. Very hard. That's where all the work goes. But they were able to come up with this cut and identify these signal events as electron neutrino appearance. And they measure the spectrum, and it agrees with the muon neutrino spectrum, as they expect. So they get the right answer for electron neutrino appearance. I didn't show you the formula, though, for electron neutrino appearance. It doesn't just depend on sine squared theta 1 3. It depends on delta as well. It also depends on the other values of the angles. When you put all that together, this contour, this curvy line rather, shows you the sine squared 2 theta 1 3 that's best fit from T2K with some uncertainty as a function of the CP violating phase delta. This is our result, which doesn't depend on delta. We integrate that out. There's some indication that delta is not equal to 0. It might even be maximal. Right? It looks like it's close to pi over 2. That would be stupendous, right? These guys know this. They're working on their experiment to try and figure out where to run next. The key would be to flip polarity and to start looking at nu bar appearance instead of nu E appearance. It'll go the other, you'll basically flip to the other side of the curve, get a bigger effect, though with less statistics. That would be very, very exciting. We'd actually be measuring CP violation, and it would look like it'd be a huge effect. Neutrinos are so different than quarks, it's amazing. It's not surprising, they get their mass from an entirely different mechanism, right? Neutrinos do not get their mass from the Higgs mechanism. Don't let any of the press fool you. They get their mass most likely from something called the seesaw mechanism, which we can talk about later. So there's a lot of experiments on the horizon that people are working on. We're collecting more data, so is Reno. Double Show should have their second near detector up soon. T2K is taking more data, they're going to reverse polarity. NOVA starts taking data soon. A great big experiment called LBNE is moving forward, will hopefully be put underground in South Dakota. Neutrino double beta decay at the ton scale is going to be critical for pinning down that neutrinos are in fact Majorana particles, or so we hope. Knowing the mass hierarchy is important for all this, and there's a reactor experiment which we used to call Daya Bay 2, but now is called the Jiangmen Underground Neutrino Observatory. Jiangmen is in China. Here's Hong Kong up here, here's Daya Bay, Jiangmen is down here. Two big reactor complexes on the coast here, putting it at a distance away where you're sensitive to the theta 1-2 oscillation, like Tamland. But now the trick is that we have theta 1-3 oscillations on top of theta 1-2. And they either look like this red curve or the black curve, depending on whether the hierarchy is normal or inverted. So the idea is to measure that neutrino spectrum and detect the phase between those two wiggles in a detector that is 35 meters across under the ground. It's going to be tough, but the Chinese are hell-bent on this. They're going forward. Some of us would like to collaborate, but that's going to depend on whether the Department of Energy sees fit to contribute some funds towards that. We have some specific ideas, but we'll see where that goes. So thank you from all of us. This was the collaboration meeting in January 2012 when we knew we had a result coming out that was going to be exciting, but we had to keep it quiet, so everybody was smiling and happy, which wasn't always the case. But these are our collaborators from various places. So thanks very much. Any questions you got?
Yeah, can I see the slide 36 again?
36.
Yeah, I'm sorry.
That one?
Yeah, if I try to hit it nasty to
Yeah. Different people have different answers to that question. I'll tell you my answer. There's a calibration problem, right? You're taking the ratio between two different detectors.
Right.
We've got to know those energy calibrations in each of them carefully. They're close, but they only have to be off by a tiny bit to get that little bit of difference. Integrating, I'm not worried about. That's what that number is. This ratio comes from integrating. I would actually be interested to see, now that we've nailed the energy calibration, this is 2-year-old clock now. This is what appeared in our paper, the NIM paper that compared the detectors. You want to see what this looks like now that the energy calibration is done. I should probably bug somebody for that. But I think we just didn't know the energy calibration well. That's probably not the official answer.
If you're right, you could probably measure your energy calibration from this plot.
That's right, the relative
It looks
energy, you can do
roughly
that.
linear.
Right, so you just put a linear and put that's the correction factor. Could be, I mean, it would be one way to do it. But I think we redid everything for the new analysis. So all the calibrations redone, so the data was passed again through and all the new calibrations put in. So this really is a whole piece of it. Any other questions?
So do you know the Korean experiment race?
Yeah, it's called Reno 50.
Right.
They want to do the same thing as Juno and go some distance away. They had a workshop, they're planning on it. I don't know too much more than that. I think if we've got a chance of convincing the U.S. funding agency that we should do this, it would be for Juno and not for Reno 50. one of the problems that experiment had, I just alluded to it, but the fact that we have all that extra overburden really got us to the point where this nasty, nasty background, which gives you neutrinos up to 10 MeV, that underlies things. We know that background. We really feel we have that pin. Double Show also did a good job in pinning that background. Reno submitted their PRL right after ours went out. And I was a referee of their PRL. I really wanted them to include the same sort of plot that showed how it should depend on energy, because they had, I think, a lot of background left. If you look at, I've got it in here on some other slides, I'm not going to worry about it, but if you remember, oops, I made a big deal about how this was the result of the best fit. If you look at their data, they had this big lump in here, in this ratio, and I think it's because they had lithium-8 background, lithium-9 background that they had not subtracted, not had accounted for correctly. You know, we were trying to make sure that theta 1,3 was non-zero, we had a right answer, so I said this paper should be published. But I said, you know, we really should include this so we could talk about it. They didn't want to. Go ahead. But I think the problem, the fact that they haven't been able to really clean up the backgrounds and make sure they know what's going on, I think in the back of some people's minds, that's a deterrent to building a bigger, larger, more difficult experiment. You can't get the smaller one to really have everything nailed. I mean, I really like this experiment we did, but I had very little to do with it. A lot of really smart people spent a lot of time, and every systematic uncertainty was pinned. And that's one of the reasons I think it worked out so well.
So what were the final uncertainties on your data, your numbers?
Well, this is our best answer for theta 1,3.
So, okay, the uncertainties, how much of those are statistics? and
It's
how
all
much-
statistics.
All statistics.
Yeah.
Is that saying that you should loosen it up to get more statistics? I mean,
Loosen it up and loosen up the cuts.
You loosen up the cuts. I mean, that's usually the game we play. Is that
Yeah.
if you're completely dominated by one, you may not be out.
I gotta look, but I think by the time we remember, this is all based on 6 ADs, 6 anti-Dutrient detectors. We have more than a year's data in the can now with 8 detectors.
Okay.
So that is not only more time, it's more data per unit time.
Right, okay.
And we want to run another year and a half. So before we screw around with that, I think we want to see how much data we actually have.
Yeah, if you've got a lot more data coming in,
Yeah.
it has the advantage because it's different. It also tells you that you trust your answer a lot more, which is worth a lot. But
We'd like to hit those systematic uncertainties.
right, sort of like the plot of systematic uncertainty versus some cut threshold.
Yeah.
Right, the statistical and the systematic, and you watch them cross each other, and then you
We
figure where
could
you're
probably
at.
pick up some more, I have to think, probably some way, probably the neutrons is the place to get a little bit more. But I'm not sure how much we get and how much it'll cost us.
Yeah, and I think group box because it looks like you were losing, you might be losing a factor of 2 just in your.
Yeah,
your
one of the
neutron.
things to do is an independent analysis, and this is happening too, is to do an independent analysis with this data. And a couple groups are pursuing this. We've got all of this above a certain energy, totally independent data set, total different systematics, neutrons, capturing, and
Could that be where your neutrons are going?
Some of them are, obviously.
Yeah, I mean, in some sense, that might tell you.
Yeah.
In some sense, at the entrance, you're getting them there.
Yeah, that's
Doing
right.
something else to knock down your neutron interaction length is not going to help you at all.
I'm not sure. I mean, there's obviously a lot more protons in this thing than there are gadolinium nuclei. But, I'd have to look at the numbers to see, but there's a lot of events here.
That's brighter.
Yeah, you're right.
It's pretty darn bright.
So, yeah, there are a lot of them in there.
Somebody's next.
Your question?
Yeah, for the new proposed experiment with the over 30 meter, I guess it's your scintillator. Are you going to have to develop a new scintillator because you're starting to run into your
Oh,
length is.
good question. Yeah. John points out that our 30-meter attenuation length is the size of the Juno detector. Really good question. I'm not sure what the plans are. LAB looks like a nice material because you can put it underground and safe and all. It might be that we're not talking about doping with gadolinium. We might rely on the neutrons captured on protons for Juno. That'll help. That'll get you some back. But the LED itself is 45 meters attenuation length. And that can help you a little bit because that'll sort of tell you where the events were. You can use that in timing to make corrections. But Juno is an experiment that needs better than 1% energy resolution to see those little wiggles. And that all has to be calibrated out. If you've got a 35-meter attenuation length and something that's 35 meters big, then you've got 2.7, a factor 2.7 change from one side to the other. You got to calibrate that out if you're going to see a 1% effect. That's a real challenge. And that's where a lot of the work is going to be. So, it may be that the little bit extra you get this way is only going to help you so much. You're still dealing with, even water, is 90 meters, so it's going to do so well. That's going to be the real challenge of Juno, getting that calibration.
When is the construction due to start with Juno?
Chinese are going full bore ahead. They've picked the site. They're getting the civil engineering in there. One of the things that's interesting from an experimental point of view is that the U.S. contribution to Daya Bay was about $30 million, something like that, 335. A lot of that cost went to buying photomultiplier tubes because at the time the only real manufacturer of good photomultiplier tubes was Hamamatsu, and they would only take dollars and pay RMB. So that's where a lot of that money went. The Chinese have built some excellent facilities in the U.S. and in China they've bought some companies. They now make high performance photo detection devices, and they're going to make all of the photomultiplier tubes for this. So they've already started contracting on that, and most of the work for Juno is now trying to figure out how to build the shell, what it ought to look like, how you might construct it. There's a lot of R&D to go, but they're not afraid to go this with China and collaborators from Germany, Italy. A lot of the underground people are excited about doing this, even if there are no U.S. collaborators. Yeah, problem.
When I look at this plot, when I look at your backgrounds, I see potassium-40, I see the lead-208 first excited state from the uranium chains.
Okay,
But
yeah.
what's the stuff above?
Help me here, Carl. Let's see.
The upper yellow band there at 2.7 MeV.
Yes.
That guy, that's the lead first excited state.
Yeah. Okay. Lead
That's
first excited
that's from the end of one of the fission chains.
No.
Well, what's the echo above that? I
So
see
this is 2 point.
well, below there, the thing at 1.5, that's potassium
No, I
40.
think that's
Then
thallium.
the thing at 2.7, that's.
No, remember, we don't see the reactor core, so.
No, but you always have some amount of uranium in your rock.
Maybe that's leaking through, that's possible. You have to capture that
There's
inside memory.
thallium-208, that's it.
Thallium-208,
That's the
that's
first
what-
excited state in lead.
Oh, that's what you meant. Oh, okay.
And potassium-40, so I recognized those two. It was, what was the stuff above that? Because normally in the normal room background spectrum, it just drops like a rock above that.
Okay.
Am I being
let's see.
fooled by some logarithmic vertical scale or what?
I don't know, but there's, let me check something. So these are the gamma sources we use, and some of these came out of the single spectrum. So there's, all that's labeled on this plot is thallium-208
And potassium-40.
and potassium-40, except that's from the calibration source, apparently. Actually, that to mention, that might be mislabeled. That could be from the single spectrum. I'm just looking at this. I don't know. It's not labeled on this plot. Someone didn't pick it out. I don't know.
As I said, normally above the thallium, it's the beta decay of thallium to lead-208, first excited state. And that gamma ray normally is the last room background line. And then your cosmic rays.
Yeah, I don't see it on these. Or was it about, it was above that, right? Let's something in
There
here.
seemed to be some sort of,
Could it be a shoulder? Could it be a Compton edge from one or more of the gadolinium captured gamma rays? Gadolinium is several gamma rays, right? So, I mean, that, if I look at this, I'm seeing what looks like a Compton edge.
maybe.
I don't know. I'll ask some people.
You have. Can be seeing an elastic excitation curve.
Is that 4.4?
4.4.
Oscilloscope. I would expect to see that in here. You know, some of the things we could look at. So that comes from a neutron. Actually, you've got a point. Because if that's from neutrons scattering from carbon, then even though it would not show up so easily here, when we look at it in delayed coincidence, you're picking up that neutron, and maybe that's what you're seeing. That's possible. It could be. Let me ask around. Someone may have already thought about that.
I mean, clearly, it dropped off quickly above there, but you were seeing what looked like maybe one or two more lines above.
Could be. Could be. If that's the case, we'll try and analyze it, get more energy calculation.
Well, and it looked like that was that echo stuff that was gonna dictate the lower limit on your background for the NPD gamma.
Yeah, no, that's certainly true.
So if you can
It's-
understand and get rid of it, or at least understand it and count it in a quantitative
No,
way.
the guys who are analyzing this are trying hard to push the energy down, but I don't think they go below 4. So you were thinking of this echo here, and
Yep.
thinking this might be 4.4. Yeah, it's maybe. Looks about right. Could be. Good. Great. See, not having nuclear physicists. All right, thanks a lot.